All right, let's crack the code on one of the most powerful and honestly most useful concepts in all of physics: potential energy and the law of conservation. So here's the game plan. First, we'll see how different forces have their own personalities. Then, we'll uncover where energy likes to hide. After that, we'll get into the unbreakable law that runs the whole show, and finally, we'll put it all together to solve some real physics puzzles. First things first, you have to understand that not all forces play by the same rules. They really do have these distinct personalities that totally change how energy behaves. Okay, so this is where it gets really interesting. Think of conservative forces like a perfect bank account. The energy you put in, you can always get back out, 100% of it. It doesn't matter what path you take. But non-conservative forces, they're like a bank account with fees. They're always taking a cut, and the longer and rougher the path, the more energy they just bleed away. And here they are, the usual suspects. On one side, you've got your energy savers, gravity, springs. They're great at storing energy for later. On the other side are the energy spenders, friction and air resistance. These guys are notorious for taking useful, organized energy and just turning it into useless heat. All right, so now that we know who our energy savers are, let's figure out how they do it. This is where we uncover energy that's basically in hiding, just waiting for the right moment. And that's potential energy. You know, it's a special privilege that only those conservative forces can grant. It's energy that's stored up simply because of where something is. Think of a roller coaster at the top of a hill or a drawn bowstring. That's potential energy, just waiting to be unleashed. And here's the blueprint for gravity. This formula isn't just random letters. It literally represents the work you had to do against gravity's pull to lift something up to that height h. The higher you lift it, the more energy you've basically banked away. It's the exact same idea with springs. This equation is the story of all the effort you put in, fighting the spring, to either stretch it or squish it by that distance x. The more you compress it, the more energy you've crammed into those coils ready to burst out. Okay, this is it. This is the big one. The golden rule that governs everything, as long as we're in a world where only those well-behaved, conservative forces are in charge. This is the law of conservation of mechanical energy, and it's a really profound idea. It means in a perfect world, without friction, the total amount of energy, that combination of motion energy and stored energy, is exactly the same from start to finish. It never changes, not even a little bit. And this beautiful little equation is your master key to so many problems. It just means energy changes its outfit. As that roller coaster dives down a hill, its stored potential energy U transforms point for point into speed, or kinetic energy K. The total amount in the bank always stays the same. That's the critical question, isn't it? Because, let's be real, the world isn't perfect. It's messy. And those energy-stealing, non-conservative forces are absolutely everywhere, messing up our nice, clean picture. And here's how we deal with the mess. This is the more complete rule. It tells us that the work done by friction is exactly equal to the change in the total energy. So the energy doesn't just vanish into thin air. It's just been converted by friction into something else, usually heat. Okay, enough theory. Let's actually put this stuff to work. You're about to see how thinking in terms of energy gives you this incredible shortcut for solving problems that would be a total headache otherwise. All right, a classic drop problem. Now, we could mess around with equations for acceleration and time and all that, or we could use our new energy superpower and get the answer way faster. The logic here is just so clean. Step 1, are there any non-conservative forces? Nope, just gravity. So our golden rule applies. That means 100% of the potential energy it had at the top has to become kinetic energy at the bottom. We just set them equal, and the algebra is a piece of cake. And boom, just like that, we get 20 meters per second. No calculating acceleration, no messing with time. That's the elegance of using energy conservation. It's powerful stuff. Okay, that was a good warm-up. But let's be real. Exams can get a lot trickier. So let's level up and tackle a more complex problem from an actual competitive exam. This is how you apply this thinking when the pressure is on. The secret here isn't just crunching numbers, it's the strategy. You have a total energy budget of 2 joules, and that's all you get.
So, to have the fastest speed, you need the most kinetic energy possible, right? Well, that can only happen at the exact point where the potential energy is at its absolute minimum. So you find that low point, subtract its energy from your total budget, and whatever's left over has to be your maximum kinetic energy.
Here's another type of question you'll see all the time. It looks like it's about oscillations and timing, but it's actually a clever puzzle that connects forces and energy together. So here's the trick. You have to realize this is a two-step problem. The first sentence is a clue. You have to use that information about force and distance to figure out a fundamental property of the spring itself, its stiffness, K. Once you've solved for K, that first part of the puzzle, you'll have everything you need to actually answer the main question. So as we wrap up, I want to leave you with this one big idea to chew on. We've seen how friction can make it seem like mechanical energy just disappears from a system. But the most fundamental law in the universe says energy can't be created or destroyed. So if it's not actually lost, where does all that energy from friction really go?